Okay, Borger High School, this is the fourth PowerPoint, and we're talking about chemical and physical properties, Unit 3 for chemistry. And we're on capital letter B on your notes, so find capital letter B. It should be at the bottom of page 3. Pure substances can be only one of two things. They're either going to be elements or compounds. That's it. There are only two choices on this. So if you have a pure substance, it's either going to be an element or a compound. And you know several elements are out there. You have access to them. If you have aluminum foil, that's pure aluminum. If you've seen copper wire, it's pure copper. Those are both elements. Elements are made of only one type of atom. All the atoms are the same. They all have the same number of protons, so they're all the same type of atom. Elements are the simplest form of matter, and they can't be changed into another element unless you do something really radioactive and nuclear to them. So if you want the smallest piece of gold that you can get, then you'd have a gold atom. And all the gold atoms, when put together, we say that all the gold atoms are basically alike. They have the same number of protons. And so they're considered to be an element. Now, you can't break elements down by normal chemical means. I mean, you can throw acid on whatever, but they're not going to break down into smaller pieces or into less simplified or less complex pieces. So normal chemical reactions can't break elements down. Now, nuclear reactions are not considered normal chemical reactions. So we're not going nuclear here. We're not going to be talking about radioactive material, things like that. There are 112. If you look at the periodic table that typically is in the front of the room, you'll see that it's got 112, 113, 14, 15. Some of the last ones don't have normal element symbols for them. We've got 112 that have been discovered, but only 109 have been named and their names accepted. However, this is constantly changing, so it just depends on the date that your periodic table was made. There are only 92 elements that are naturally occurring. All the other ones are man-made. They're created in the lab through nuclear means. They take pretty much one radioactive element and they smash it into another radioactive element, and they get some interesting things coming out of that. A lot of times the new elements that are man-made, they don't last very long. They have, they can last, they have a short half-life of maybe 30 seconds or something along those lines. You have to look at each of them, but they're kind of strange. But the naturally occurring elements, you are familiar with many of them. Now, all of these have a symbol. The symbol for the element is one capital letter printed, or one capital letter and one lowercase letter. So sometimes it's made of one letter, and sometimes it's made of two letters. If it's two letters, the first letter is capitalized, the second letter is never capitalized. Okay. The oldest known elements have their symbols taken from the Latin names, and so you can find some really weird names in there. Like we call it iron, but if you look at the symbol for iron, it's Fe, which comes from that old Latin stuff, ferrous or ferric. Okay, a few hundred years ago, leading chemists decided that symbols for the elements should be the same no matter what language you're talking about, whether it's Chinese or Latin or Greek or English or Spanish. They said, look, we've got to get these symbols all the same so people know what they're talking about. So they all agreed that the symbols would be taken from mainly Latin, which is a dead language. And when I say dead language, it means nobody on the planet is speaking Latin as an everyday language. So everybody could agree with that. And so when you see the symbols on the periodic table, they're taken from the Latin word for the element, or mostly from the Latin words for the elements. It just so happens that our language, the English language, is based a lot on the Latin, and so it looks like English to us. When we see the symbol for boron, it looks like a B. You don't necessarily see a symbol, and you guys have seen like a language written in Russian. You've seen really strange letters and stuff. You don't see that. You see it based on the Latin alphabet, and so it looks like it's English to us. You'll notice too that it's never, ever, ever written in cursive because there was no such thing as cursive for the Latin language. So it's always in print. So you print it, the first letter is capitalized, the second letter, if it's got one, is never capitalized. All right. Next one on your notes, if you look down, that was free information. Aren't you so happy? Free information. Next one on your list is in the middle of page 4, and it's an atom. It's the smallest particle of matter which still retains or has the properties of that element. So the smallest piece of gold that you can get that still has the properties of gold is called an atom. When you take that atom and break it down smaller, the parts of the atom, the protons, neutrons, and electrons, all the individual pieces look the same. So you can line up electrons from all sorts of elements, and they just look like electrons. excuse me, you can line up protons from all sorts of elements and just, they look like protons. It's the combinations of the protons that really tell you or give you the personality of the elements or the characteristics that the elements have. So when you take that atom and you break it apart, the individual pieces all look alike. It's kind of like saying you take a human and you pull the cells out and you look at the cells, and the cells of one human look the same as the cells from another human. Yeah? It's when you put everything together that you get the differences that you notice. Number 2, atoms are very, very, very small. They're typically about 1 times 10 to the negative 8 centimeters in diameter. Pretty small. 1 gram of lead, 1 gram of lead contains 2.9 times 10 to the 21 atoms of lead. By comparison, the Earth's entire population is only 5 times 10 to the 9th. So look at that. 2.9 times 10 to the 21, and compare that to the whole population on Earth, 5 times 10 to the 9th. There's a huge difference there. And the reason the numbers are so high for the numbers of atoms is because they're so incredibly tiny. Now, we had atoms, we had elements, now we have compounds. Compounds are substances that are made of more than one type of atom they're chemically bonded together. So it's got to be more than one kind of element. Compounds can be changed to other compounds. They can be separated by chemical reactions. They can be created by chemical reactions. And you don't need anything weird or strange or radioactive or nuclear to get those reactions to occur. When we talk about reactions in chemistry, we're not cutting down inside the nucleus of the atom. We're staying on the outside where the electrons are. So we're going to share electrons, we're going to transfer electrons, and do stuff like that. We don't need nuclear stuff to do chemistry. Number 1, compounds do not have the same properties as the elements which make them up. So let's say we have hydrogen and oxygen, and we combine them to get water. Water, you guys all know what water is. You know, you've had experience with it. And yet if we take those atoms apart again, hydrogen is a colorless, odorless gas. It's very, very flammable. Oxygen is a colorless, odorless gas. It's very, very flammable. You put them together, you get water that we have to survive. So when you create a compound out of 2 different elements, or more, you can have 2 or 3 or 4 or 5 different elements, you create something totally new. And there's your lovely example right there. There are over 10 million different compounds that are known today, and most of those are organic. And if you remember, organic means they have carbon in them. We're not going to study much on the organic chemistry in this class, this first-year chemistry class. We'll focus on inorganic, those compounds that don't have carbon in them. The chemical formula for a compound will have more than one capital letter in it because it contains more than one element. So remember, the symbols for the elements, one capital letter, and if there are 2 letters, one capital, one lowercase. When you have a compound, you're going to have more than one capital letter. That tells you that you're going to have more than one element in there. There it is again. Someday that'll go away. Letter D, the law of definite proportions. The law of definite proportions, or ratios, says that elements in a compound, the ratios of them don't change. So water will always be 2 H's and 1 O. If it's 2 H's and 2 O's, don't drink it. It's not water. It's H2O2. Do you guys know what that is? Hydrogen peroxide. You know that stuff in the brown bottle you can buy at Walmart, and you put it on scabs or sores and it'll bubble up? Well, you don't want to drink that. So H2O2, 2 hydrogens to 2 oxygens, is not water. Just because it's got hydrogen and oxygen in it doesn't mean it's water. In order to have water, you have to have always 2 H's to 1 O. If you change the proportions, it's no longer that compound. So what this law says is that when you have a compound, the proportions of the elements within it are always going to be the same. Now, here's another one. Here's the law of multiple proportions. And that means that you have elements and they can combine in different ratios to get different compounds. So you have H2O, and you get water, and you have H2O2, and you get hydrogen peroxide. They can combine in different ratios. Here on the picture you have carbon and oxygen, and you get carbon monoxide, the stuff that's blowing out of the exhaust on your car. And then you have carbon and oxygen, and if you have 1 carbon and 2 oxygens, you guys know the stuff that comes out of your lungs is carbon dioxide. So multiple proportions, which means that you can have the atoms combining, or the elements combining in different proportions to get different compounds. All right, here we have some lovely pictures. Elements, compounds, and mixtures. In the first one, if you look at the jar that's on the left, you have the hydrogen atoms. Hydrogen usually is never alone. It's kind of like girls going to the bathroom. They never go alone. Yeah, they always have to have their friends with them. Well, hydrogen is never alone. It's always bonded to another hydrogen atom. So you have the element hydrogen. If you look at the second one, you notice that you've got a large atom, a large purpley colored atom, and then the two little yellow ones. So you have oxygen and you have hydrogen, and they're stuck together, so that tells you that they're bonded together. So you've got water, you have a compound, and you can see, and they've just stylistically drawn it this way for you, that you have different substances that's in there. It's all water, so it's a pure substance, it's a compound, but you can see that the compound itself is made of different atoms. If you look at the third one, now you've got the two little bitty yellow hydrogen atoms, and you have the two bigger oxygen atoms, but they're not combined together, they're just kind of mixed in with each other. So on the third one, what you have is, oh, it skipped over the third one, what you have is a mixture, hydrogen and oxygen as a mixture. And then you look at the fourth one, and you still have a mixture, you just have more hydrogen than you have oxygen. These kinds of pictures you'll see on the tax test or on the end of course exam, so be aware that they'll show you something similar to this, and I'll show you some of this stuff in class too. Alright, you have a matter flow chart that you've drawn in class, and when we look at this matter flow chart, we can go through here and say, okay, we've got graphite. Graphite's what's in your pencil. We call it pencil lead, but it's not lead anymore. Lead's poisonous. Little kids are stupid. They eat it, so they figured it's a good idea to not have pencil lead anymore in the pencils. Instead, we have graphite. Works really well. Graphite is actually made of carbon, and so it's an element. Pepper. You look at pepper, you dump some out in your hand, and it's got little black flecks and little white flecks. Can you see parts with different properties? Yes. So it's a heterogeneous mixture. Sugar, you pour some sugar out in your hand, it all looks the same. Sugar is actually I'm going to mess this up, C12H22O11. Messy compound. But it's all one unit, it's all one compound, it's a pure substance. Paint. I don't know about you guys, but I bought some paint last summer, and so I've seen paint when it's been sitting there for a while. And if you've ever taken the lid off of paint that's been sitting there for a while, oh my gosh, it doesn't look at all like the color you bought. And so you have to mix it up really, really good. Paint is a mixture, and if you let it sit for a while, it will unmix. And then the last one of my favorites is soda, Dr. Pepper. Dr. Pepper rules. The soda is a solution. And, some people will say it's a solution because it looks the same throughout, a nice liquid thing, but you can see bubbles in there. So, sometimes there are not nice, strong, dark boundaries between what's a solution and what's a mixture, so we have to kind of look at things.